Good to know. Yeah, thank you very much, Netjeka, and thank you very much, Santi, for the technical organization. So this, okay, all the technical details. Here we go. Now, this is what Netjeka just said. Yes, I understood. But now we can start, I assume. Okay, so that's in brief what Netjeka said. So we do have the same introduction, more or less. And I just should mention that Netjeka had the great idea to initiate the seminar. And Hans was the first speaker last year or so, and then Hans talked a number of other colleagues into it. And we are going to write a book about this. But first we try our ideas here with the audience. Because what do we want to do? First of all, we do not aim at a concise history of climate research in Hamburg. But that's already done in an essay Hans and I wrote for the book, university book of the University of Hamburg, 100 Jahre Universität in German, unfortunately. We rather here, this will appear, by the way, soon, this year, with 5 years delay. Now we here aim at describing ideas and the background, the embedding in the international science arena that have been suggested by scientists while working here in Hamburg, and that have seen some repercussions or taken up by the international science community. Surely the selection of topics we have chosen is really subjective, but that's the way it is. Other authors might have about different topics. So therefore, though it's subjective, we welcome comments and suggestions. You might have overlooked something, or might have just a different test perspective. That's something different, but you don't want to make really errors and oversights. Okay, now the topic today starts with a statement by Klaus Hasselmann on flip-flop transitions and paleoclimate. And I will discuss the statement, which I will present in a minute, by using 3 examples. And the discussion follows the same structure. We start with some early setting, early simple models, early ideas, data, and then they switch to complex models, or state-of-the-art models, and then the story continues. And the 3 examples are Snowball Earth, or White Earth, Atlantic Meridional Overturning circulation, and climate-vegetation interaction. So this is a statement. In his inaugural paper in 1976, Klaus Hasselmann wrote, that was a paper on stochastic climate models. Actually, he wrote this paper when he just became the founding director of the Martin Clausen Institute. It was just a perfect start. And in this paper, there's an interesting sentence. It reads, the basic difficulty of unstable feedback models, apart from, or possibly or because of, the high degree of idealization, is that they tend to predict climate variations as a flip-flop transition, and therefore fail to reproduce the observed continuous spectrum of climatic variability. Sure, at that time, the models were mostly highly idealized, and they do not exhibit any free variability. Or if they didn't, or some were then, then some stochastic noise was prescribed as a substitute in some models. So the question is really well taken, are these flip-flop transitions that the models show just an artifact of 2 simple models? You can also turn this question into a corollary questions. Can models with a lower degree of idealization, often called complex models or quasi-realistic models, which produce a more or less realistic climate variability, show unstable feedbacks that lead to multiple equilibrium solutions and realistic flip-flop states, transitions. And this question could have also been posed by Klaus Hasselmann himself, because at the end of the 1970s and early 1980s, he fostered the construction of numerical models of the climate system. And perhaps as a personal side note, in 85, I was a postdoc with Klaus Hasselmann, and then I left the position to get a permanent position in a research center nearby. And Klaus asked me, what do you want to do? And back then I was boundary layer meteorologist and said, I would like to study boundary flow over heterogeneous terrain, and I like the idea with the stochastic ansatz. And then Klaus said, if you want to get some real numbers, construct a numerical model. Okay, and I followed this advice. Okay, so this is a corollary question could have been posed by Klaus himself. Okay, here are the examples. We start with the Snowball Earth, and it starts with a prediction by Mikhail Budico and William Sellers, independently of each other. They wanted to, or aimed at understanding the glacial cycles, the quaternary glacial cycles. And they explored the consequences of an ice albedo feedback in the presence of slight variations in the solar constant. And they used the energy budget, so internal heat is equal to insolation, or mean annual insolation modified by albedo, outgoing heat radiation, and some advection terms, so local advection or meridional advection of heat. In an equilibrium, this is of course zero. And the advection term is parameterized in terms of local temperature and some planetary temperature, where then in this equation the advection vanishes. Okay, and independently, Budico and Sellers found something like this, and I copied this figure from the Budico paper. They found a sensitivity of temperature, or phi sub 0 is the ice boundary, which varies with geographic latitude. And they change the insolation, and then you have some sensitivity, and above a certain threshold, or now there's tipping. Tipping point is a really old concept, goes back to the 1950s. So beyond a certain tipping point, then all of a sudden the Earth plunges into a frozen state, or the ice just jumps all over the planet. So this was called a climate catastrophe. Surely it happens, it would also be a catastrophe for humankind, as Budico himself claimed. But sure, it was also a reference to the development of the mathematical theory of climate or catastrophes by René Thom, Vladimir Arnold at that time. Klaus Fraedrich, back then he was in Berlin, but then came to Hamburg. He, I think, was one of the first climate researchers in meteorological department, because before the predecessor, they said we would like to do physics of the atmosphere, not so much climate. For example, like Hinspeter, the predecessor, he said, I'm not a climatologist, I'm a meteorologist, a physicist. I don't know where the difference is, but anyhow, so Klaus, he investigated climate catastrophes using the mathematical model of catastrophes. And I show these equilibria, state space, and then the bifurcation diagram, and the potential of this dynamic system, because it also has this repercussion in art. No? I mean, Salvador Dali painted the swallow's tail in the early 80s, actually as a homage to René Thom. But if you look at these figures, it could also be a homage as climate research or Klaus Fraedrich. Okay, what about simple climate models if you add noise, some variability? Peter Lemke was a doctoral student with Klaus Hasselmann at that time. So he used the Budico-Sellers model, but he added a stochastic term, so weather noise in a way. Therefore, the temperature would become a stochastic variable, not a deterministic one. And then he could explain the observed, or I should say reconstructed spectra of temperature on timescales from decades to 10,000 years roughly. Now, the interesting point here is that he writes that there exists a critical value of the albedo feedback, beyond which the spectral response becomes infinite. I would interpret this as, also in such a model, there is a possibility of a flip-flop transition. Martin Clausen, I mean, he was research scientist with South American Sinspeter before he became director. Actually, was the department on climate processes. So, but Martin Clausen, as a sidestep, did also some climate dynamics in one of his papers. Actually, that's his only paper on this point. Martin Clausen, he took up an idea by Fraedrich to relate the advection term A, not to some parameterization, but to an optimum principle. So assume that the entropy production should be maximized. So you somehow related the advection term to the entropy difference, change in entropy, incoming, so Q insolation to temperature of the sun, entropy flux of the entropy of the insolation, and to the outgoing heat radiation divided by temperature. That's the entropy change. Don't want to go into detail, but this the interesting point is that the resulting sensitivities from that more complicated model partly agree and disagree with those of similar energy balance models. The disagreement is particularly high if the albedo feedback is included. That's strange, because in the other models it was just the opposite. And the feedback is strongly reduced because of the opposing effects of cloud amount in high latitudes. So, including more complexity would get rid of flip-flops. What about more complex, or back then state-of-the-art models? And Richard Weatherald and Suki Manabe were, I think, among the first, or perhaps the first, to set up a numerical climate model, a really simple one, a limited area model just of the atmosphere with idealized topography, periodic boundary conditions, no heat flux in the ocean, fixed cloudiness, and then they did some sensitivity experiments. We found a high sensitivity of hydrological cycle to small perturbation in the insolation, plus 2%, minus 2%, minus 4%, but no flip-flop, which appeared in the simple energy budget models. Okay, that was the first result, the main result. But if you look at the appendix of this paper, they also address the question of what they call the white Earth solution. So they started the model with a high planetary albedo, so something you find in Antarctica, 0.7, with the isothermal model sub-freezing, really freezing, minus 53 degrees Celsius, and you let the model run. And the model would stay there. So they concluded that the white Earth solution might be a stable solution. Okay, now this is all theory. Playing chess and whatsoever, having fun, but things shifted really at a higher gear when geologists really detected snowball flip-flops. Now we know there were at least 2 snowball Earth during the last billion years, some 720 to 660 million years ago, the Sturgeon, and 645 to 635 million years in Meridional. Snowball, the Sturgeon, and Meridional refer to rock formations in Australia, where they are most pronounced and which are used as a reference for the geological settings. And this figure, experts would recognize this, show that the change from an ice age for snowball to a green Earth appeared abruptly, geologically speaking. And the idea was, yeah, there was some interplay of the variation in weathering and volcanic outgassing. And this is a sketch drawn by Paul Hoffmann and back in the and if you would like to read more, I refer to a paper, a more recent review paper by Paul Hoffmann and many others. And yeah, you can check this geological idea by using what we know already. So assuming that the atmospheric CO2 content, C, depends only on volcanic outgassing, which might be constant over a few million years, we are constant. And then the weathering, which, however, is a function of carbon, or CO2, and temperature. And then, yeah, of course, you use the energy budget model. Albedo is a function of temperature, and the heat variation is depends on CO2 and temperature, like in the model by, for example, Klaus Fraedrich. And then you get the flip-flop transitions. This example I showed in all my paleoclimate lectures, and sometimes also in the exercises, just to bother the student to recover them and to learn that, yeah, you get these flip-flop transitions, but they depend on the numerous parameters, mainly the albedo parameterization in the model. And then you can get them, or you can get them, you get stuck into the snowball or the hothouse. I mean, it's really hard to get, but it's, yeah, it's more a check of concept, no? Nothing else. It's just another highly idealized flip-flop transition model. But when the papers by the geologists appeared, of course, the theoreticians started their simple models. They're like this one here, and some of them also of intermediate complexity, which don't have any variability or so. And yeah, I think the first to ask the question, now, do we see snowball flip-flop in our state-of-the-art comprehensive climate system model? Was Jochen Marotzke and Michael Botzet. They used a good old MPI ESM and switched off the sun. Not completely, of course, because model codes do not like zeros. So they reduced the solar constant considerably, and they found that temperature, the Earth get really cold. The blue colors are subfreeze temperatures, and now that's after 9 years. Only the tropics are ice-free, and after 19 to 20 years, the Earth is completely frozen by sea ice. Or didn't have ice sheets. Okay, now that's good, but that just proves that the model is great. It survives the climate catastrophe. I mean, try it with other models, no? But it's not so easy. So that's a great model, the MPI ESM. Okay, but this is more interesting. It shows various solutions and flip-flops. So the light blue is the control simulation, present day. Then 19 years of darkness, so the constant goes down by to 0.1 per mil. So after 19 years, it freezes. If you switch on light by the sun, before the Earth gets completely frozen, yeah, then you recover. But if the Earth is frozen after 19, 20 years, on the sun, then nothing happens. It stays right in Earth solution. Okay, how to get out of the snowball Earth? Well, we can raise, of course, CO2 by a factor of 10. Well, it doesn't help. By a factor of 100, it works. So this was really the first time that we see these flip-flop transitions also in a state-of-the-art complex numerical model. And it opens a new area for snowball Earth dynamics because it continues with a number of publications, and I cite only here those that appeared in my favorable paleoclimate journal. That was the past. So, and I like specifically the last one by Leonard Rummel, his PhD, just recently finished, because that is the first time Leonard produced with the new ICON model a full snowball Earth cycle, also only with sea ice, not with ice sheets. But it contains physics and chemistry, the ocean. And thereby, he proved that the ESM can now be used to study processes of Earth for Snowball Earth transitions. The reason you probably must think, the models are good, either are too simple, but the complex models are just too slow. I mean, you can, well, they are good for equilibrium simulations. No, they are not. You can study the transitions and you can derive at physically and chemically consistent constraints for the interpretation of paleo data. Okay, I should mention that meanwhile, the coupled climate ice sheet models exist, and they also show multiple ice sheets. No? Our climate model from Potsdam shows this. Actually, it shows 3 states, something like today, and then Quaternary ice age, and then Snowball Earth. And Irene, Vizcaíno, and Uwe, they also found multiple equilibria in their more complex system. Okay, that's the first example. Now the second, and that will be faster. It also starts with a prediction from simple reasoning, from theory, by Henry Stommel, also in the 1960s. That's amazing that this tipping stuff was always done in this late 50s and early 60s. By the way, the term tipping point is from social dynamics now. So it's in end of 1950s. But that's another story. Okay, Henry Stommel looked at a fluid of different salinity and temperature. So 2 big vessels, this one and this one. For symmetry reasons, this has S and salinity S and minus S. And inside the big vessels, there are 2 smaller vessels, only separated from the outer vessels by a porous wall. And it's well mixed, so it's homogeneous. And the inner vessels are connected. And then you can set on a thermal circulation. And the numerical problem, the numerical model, yields this phase space, temperature, salinity, and we see 3 equilibria, A and C, and they are stable, so attract the solution. And one repeller here on the 7 node is E, which repels this unstable solution. Okay, that's theory. And as in the last example, the theory people got excited about the theory when they saw something flipping in nature. So Hans Oeschger detected some fast transitions in the last several groups. Was it? It's 10, 13,000 years in the Gerzensee in Switzerland, and Willy Dansgaard in the ice core in Greenland. Well, this is 100,000 years, 10,000 years. It's a flip transition. That appeared in the early 80s, and when these data reconstructions appeared, sure, a number of people. Today, of course. We know that there are many of these flip-flops, and in honor of Oeschger and Dansgaard, the bomb events, interstadial, what we call it, are called Dansgaard-Oeschger events. There are many of them, at least 20. And then there are the cold events, interstadial, and some of which are particularly interesting because they carry with it a lot of ice-rafted debris. So there must have been a massive iceberg carving, and this was detected by Hartmut Heinrich, another scientist from Hamburg, with truly amazing climate stuff born in Hamburg, but that's another topic. In the early 90s, it was Wally Broker who asked, does the ocean atmosphere system have more than one stable mode of operation? Sure, in the reminiscence of Henry Stommel work. And many people jumped on this with model of intermediate complexity or conceptual models or whatsoever. For example, Jochen Moronski was I'm not sure, a PhD student or already postdoc with Jürgen Willebrand. Jürgen Willebrand was a research scientist in Klaus Hasselmann's department before he became professor in Kiel. Pierre Wielander was a frequent guest in Hamburg. he was known for this oscillation. I think he once showed this strong oscillation in Hasselmann's swimming pool, such that it was just exciting the normal modes and just getting an overspill of the swimming pool. Anyhow, so this is the idea to deal with the thermohaline circulation in model of intermediate complexity. Now, the first who studied things in a complex model were Suki Manabi and Stauffer, and independently, I'm pretty sure, Ernst Meyer-Reimer and Nikolajewicz here in Hamburg. Now, Manabi and Stauffer, they coupled atmosphere model with the ocean model. They need a strong flux correction. Presumably also has something formed in Hamburg, the Hasselmann's sailing docks. If the model drifts, just take some energy and put it and to keep it stable. Robert Sause will talk about this. But they found then eventually the on and off state of the Atlantic circulation. I like specifically, I like very much the paper by Meyer-Reimer and Nikolajewicz, because they use an ocean model and try to explore the sensitivity of the overturning circulation by injecting fresh water at different locations where geologists thought there were some freshwater inputs. And also, you cannot see the numbers here, but these are real sphere drops or realistic sphere drops, realistic mass fluxes of fresh water into the Atlantic. And you see also here these flip-flops from an on state to an off state, now here in terms of the heat flux. So here we really see a realistic sensitivity of small freshwater perturbation to the system. In a way that refutes a much later paper by Paul Valdez, who said, yeah, all these complex models are just construct for stability. Not really. Some of them are pretty sensitive and show realistic sensitive to a small perturbation, like this one here. Okay, now the story continues. I guess most of you know this figure, but there's this movie, but I will show it anyhow. I have some time still, because it's a movie here from Hamburg. I think perhaps it's really the first fully comprehensive atmosphere, ocean, continent uplift, vegetation, simulation. Only it's not coupled physics and biology chemistry. No? You see the ice sheets, the Heinrich events coming out. Dark means fresh water and here more salty water. And even the vegetation runs a bit too fast here, perhaps. But the Sahara gets greener, which I like very much. The only thing that doesn't change are the soils. Okay, that's not there. Yeah, I show this because I'm pretty sure that sooner or later we can run such models much longer and really show the details of tipping. No? Okay. Yeah, now I come to the third example. Vegetation climate states. And it also starts with predictions. The first of which is somewhat hidden, because it was set up by Andy Watson and Jim Lovelock to show a homeostasis. So that's the opposite of flip-flop. No? Because Jim Lovelock set up the so-called Gaia theory, stating that the biosphere would interact and would not only be affected by the environment, but would also affect the environment for its own sake in a way. So by and for the biosphere, so that there's an optimum growth of the biosphere. Of course, people were pretty critical about this stuff, because why should the biosphere have such a teleological foresight to just tune the environment for their own sake? And then Andy Watson and Lovelock said, no, it's much easier. That you can envision simple physical chemical feedbacks which keep the system stable. So therefore, they set up this so-called daisy world, a simple world consisting of climate and plants, daisies. One are pretty bright, so more reflectant than the environment. Others are pretty dark, much darker with a lower albedo than the environment. And they called it a parable of daisy world to emphasize, no, that's not a realistic description of what's going on, but just an idea, an exploration of this feedback. Okay, and here again, this is, story starts with the energy budget model. Now here, the planetary temperature is a function of local temperatures of the naked Earth, so to say, and then the region where you find different plant types. No? V is the vegetation fraction or desert region. And the planetary albedo also is a linear sum of these local albedos. And then the vegetation model is the competition model set up by Alfred Lotka and Vito Wolterer in the 1920s. It states that the vegetation fraction can change as function of the birth rate, so that the growth function and beta times V is the birth rate, death rate. This term here mimics the competition of species with respect to place. Okay, yeah, putting things together, we can compute the temperature as a function of insolation, which becomes stronger and stronger. And the full line is the temperature without any plants on the on the planet. So the naked one. Now, the dashed line here is the solution when the dark white plants can coexist. So white doesn't need white, but a higher albedo than the environment, or dark, a lower albedo than the uninhabited planet. And then this curve, that was a curve where Andy Watson and Angel Lovelock was focusing at. It proves that there can be this homeostasis just as a consequence of this simple feedback. Now, but we know, of course, and nowadays people learn it at school, the Lotka-Wolterer equations are good for a lot of chaos. And those were later detected by Gregorio or Van Weber. Van Weber was also here, postdoc in Hamburg, by the way. And the story becomes really interesting if you look at the beginning of the biosphere at the end. So because if the sun gets hotter and hotter, then dark daisies can exist because they have a low albedo and can make the environment warmer. No? You have two solutions. This one here is a stable solution, and then this one here, the trivial zero solution. Depends on the initial condition. When you allow seeds all over the planet, then all of a sudden the solution can jump here from 0 to this one here, of the temperature from cold temperature to a much warmer temperature. Or if you allow only niches, then the solution will stay here. And this is the unstable branch. It acts as a repeller between these two attractors. So we do have abrupt change because of the interaction between vegetation and climate, and which might be even more interesting than the homeostasis. You have the simple stuff, the same stuff at the end of the biosphere, lifespan of the biosphere. The climate gets hotter and hotter because the sun burns hotter and hotter, and only white or highly reflectant plants can exist. But eventually also these will die out. We have here stable solutions and the repellent solution. Okay, so that's a very great simple model. Now, what about complex models? Yeah, well, this is I happened when I was a postdoc with Leonard Bengtson. Leonard invited Colin Prentice when he was in Lund, and Colin and many others also set up a diagnostic vegetation model. And so when I saw this, listened to the talk Colin gave here in Hamburg at the little building, which is now wrong. Asked myself, why not just try to diagnose vegetation with our ECAM3, the old atmosphere model? Now, fortunately, the old atmosphere model was great and had a perfect hydrologic cycle, great patterns of precipitation. So I played it a little bit and found that with starting the continents all over with present-day biomes, and I don't explain the colors. Of course, this is desert here, huh? This is here. Forest, tropical forest, taiga, this is tundra. When I start the continents with a bright desert, I would get the same one, but this is start something darker. So grass, forest, and so then I get almost the same, I've got almost the same, except for Africa, which looks much greener. And that was the time I say, oh, that's strange, but it reminds me of paleoclimate. So that was my entry into paleoclimate. And I asked the diploma student, Veronika Geiger, she's still with us, to do the same, but for at the time 6,000 years ago, when the insolation was a bit different, with a stronger annual cycle of insolation, with a stronger monsoon, West African Indian monsoon, because of the stronger annual cycle of the insolation. And interestingly, she got also green Sahara, but only one state. No? I mean, independently, how to start with, we got the same sort of green, Western green Sahara. Okay, that's number one. When I published this, people try to discover these multiple equilibria and climate-vegetation models. Some didn't publish it. We don't know about it, but others did with completely different models, like Günter and Fraedrich here. They use a zonally symmetric model for the tropics. It's a much more elaborate vegetation model, not just a biomodel, which is more or less a diagnostic table or so. And you get also different, really vegetated northern Africa, going from the equator to slightly north, or in a pretty big desert, as it seems, this that we see today. Or here, Oyama and then Carlos Nobre. They did the same, but focus more on Brasilia. I mean, they are from Brazil. And you see also differences in color. So the red color is specific dry forest that you find in South America. So that was the start of Amazonian tipping, basically. Now, Axel Kleidon and others, they say, oh yeah, that's great, but no surprise that you get multiple equilibria if you use discrete biome schemes. Well taken, but. And here comes Victor Brovkin into play. He set up a continuous vegetation dynamic model. So, and this is, so to say, a simplified version for the arid and semi-arid regions. So vegetation here depends on precipitation in such a way. So if you have enough rain, it's green. If you have too few rains, it's desert, and in between this goes up. Regardless how you do it, but something like this. And then precipitation, according to what we find with our model, depends on the land cover, vegetation, more vegetation, more rain, and so on. And then you have different curves because you can have different environments, monsoon, background monsoon, rain, and so on. And then you find multiple equilibria. The Roman this one, desert, green, and so on. So you have a change in manifold of equilibrium solution with time. And then fitting the parameters of this simple model to the comprehensive or semi-comprehensive, I should say, because it's a comprehensive atmosphere model, but a very simple vegetation model. Fitting this, the parameters of this to the other model, we arrived at the idea that the Sahara was green once upon a time, and then roughly 6,000 to 4,000 years it should have expanded abruptly because you can jump from here to there, in the presence of some stochastic noise. Okay, and then later we find something in our model of intermediate complexity, which has no weather variability, but can easily go through millennia. And this is an abrupt transition, abrupt in geological terms in a few hundred years, because of a loss of stability of the green solution. It's really bifurcation. And then, fortunately, a year later, Peter de Mendock came up and said, oh, I see something like this in the dust record. Now he turned the vertical scale upside down to compare it with our model simulation. So this is little dust, and that's a lot of dust. Right at 5,500 years. So that was really the validation, the collapse of the Green Sahara was born. Of course, science continues, no? That's always great. You still find this is collapse of the Green Sahara nowadays, but a few years later, Stefan Kröpling said, no, there is no abrupt change. In his record, that's the only one in the Sahara, the pollen record, that's not abrupt, that's some variations. So no abrupt change versus this one. And then Peter and Stefan were always fighting each other. But we have modeling. So what about, what about other data? Meanwhile, we do have other data by Tim Shanahan. We worked with Tim and looked at some of his data, and here also some unpublished data. And I mean, that's all over the place, isn't it? We've got some abrupt transition and no transitions, some fluctuations and so on. So the picture is much more complicated. And that's where the story really continues. What about our complex model? The MPI ESM, our Holocene simulations. And that's the only simulations which do get a Green Sahara, at least one. The other models, French colleagues, I don't know. The Swedish colleagues, Jean Zhang, in her model, she gets now a Green Sahara, and she tries to recapture what we did a few years ago. So here we could show that indeed, this is the bare soil fraction, so desert basically, as function of time going upwards. And you see the changes here in the northwest to southeast ridge. And then Sabine Eger and her PhD could show that what we see here, the dust increase, is really linked to the dust that is uptaken here in the western part, then blown out into the Atlantic and deposited here. So that thereby she really proved the link between what we see in the data and so on. And then, Legio is here. Might be a fortuitous coincidence that just north of the region where our model indicate fast changes. And in fact, meanwhile, we know from data, but also from model, there is no collapse of the Green Sahara. It's a locally rapid, as found in data. And we also see that the heterogeneous time transgressive shift. We can explain it by using the model and so on. But the story continues because these quasi-realistic models, they do not yet realistically capture the changes in plant function diversity. A bit too simple. Okay, now let's sum up. Okay, so multiple climate equilibria, abrupt transitions, climatic catastrophes, tipping points. They now have ever fascinated the climate researchers ever since they discovered the models and data. The sociologists discovered tipping points, and they called it like tipping points in the 1950s. There was a great book by Malcolm Gladwell in 2000. The tipping point, when small things make a big difference. It was a book about social dynamic, but that itself was a tipping point because all the people are talking about tipping points. In climate science, we talk tipping points since a workshop held in Berlin in 2005. But again, the concept is pretty old. Okay, so that was a political remark. The development of complex or quasi-realistic models fostered by Klaus Hasselmann, but not only by him, but also by Günter Fischer from the Jager's predecessor. So he was one. He has also set up a numerical model of the atmosphere. Or Günter Zündermann from the Institute for Oceanography. He was a numerical ocean modeler. So they fostered the development of, almost pioneered the development of a complex model. And basically, thereby, we refuted the statement that the flip-flop transitions were an artifact of too simple. They do occur also in complex models, and we in Hamburg have contributed a significant part to this story. Of course, the story continues, no? And even state-of-the-art complex or quasi-realistic models are too simple to realistically describe some globally important processes like the vertical energy transfers and topics. And that's something here now beyond Stevens tackles with this very high kilometer scale global simulations, or the interaction between plant functional diversity or biodiversity and climate, which we started. Okay, that's it, folks. Thank you much for your attention, and questions are welcome.